Hi, I'm Jason Lacroix. I'm a principal member of technical staff here in AMD's game engineering organization. And today, it's my pleasure to walk you through our brand new Fidelity Effects SDK. Now, before starting, here's a rough outline of what I'll be discussing today. We'll first go over the reasons why we chose to modify our delivery process for Fidelity Effects features. Then we'll have an in-depth look at how the Fidelity Effects SDK works, with detailed looks at its internal components and a simple usage example. Next, we'll have a brief overview of Cauldron 2.0, the new graphics framework that powers all of our SDK samples. We'll then take a look at a few of these new samples that we're releasing alongside the first version of the SDK. And lastly, we'll have a quick look at our roadmap for the SDK and wrap things up. Now, let's go over a little bit of overview into the Fidelity Effects SDK. The Fidelity Effects SDK is our new, easy-to-integrate solution for developers looking to include our features into their games without any of the hassle of complicated porting procedures. It's effectively middleware to do the heavy lifting for the developers so that they can very quickly bring our features into their games. Over the last 4 years, we've introduced a lot of great value technology. However, it started becoming apparent that we needed a better solution going forward as we continued to grow our effects library. Our current samples had a number of problems that became more apparent as we kept adding on to it. Inconsistencies in coding standards and styles, some of which were done in ways that was not really trivial to follow along with. We had a lot of needless boilerplate code and duplication when it came to setting up new effects. There was a general lack of stability on the backend graphics frameworks. In fact, our effects to now have been shipped on no less than 6 different versions of Cauldron, each of which introduced many API-breaking changes, slowing development to a pace that we were not very happy with. We have inconsistencies in documentation formats or very little information altogether. Inconsistencies in feature accessors. Some of our samples had API-like accessors, however most did not. We also had limited platform or API support. Rarely did we ship Vulkan versions at the same time as DX12, if at all, and very few features were supported on Xbox. Now, the SDK aims to rectify a lot of this by bringing simplicity, structure, and consistency to all of the great software you've come to expect from AMD. Of note, the SDK features a consistent and standard in style that is much more user-friendly. Far less boilerplate code to write to get up and running. We've re-architected our graphical framework that is not only more robust and future-proof, but is also platform API agnostic, allowing us to develop all of our effects across all intended targets simultaneously. This also doubles as a great way to show developers how to create custom backend implementations for your own multi-platform engines to back our Fidelity Effects features. We've added extensive documentation and taken a lot of the guesswork out of implementation steps by offering complete pre-built solutions for all of our effects, most of which can be supported in under 20 lines of code. That being said, if you are a fan of taking the code we put out and manually integrating it yourself, you are still free to do that. We've not taken anything away. All we've done is move things into a more coherent structure on disk and cleaned up the code to make it more consistent in style. The SDK was designed from the ground up to be as modular as possible. This means you're free to pick and choose and support only the features you want and leave the rest behind. This modularity also applies to our backend implementation. The SDK will ship with a native DX12 and Vulkan backend and a custom backend example for our own graphics framework Cauldron, in order to show how custom multi-API or multi-platform backends can be implemented to support the SDK. We also have a DirectX 11 backend available for NDA partners for those games that still require legacy support. However, note that some samples cannot run on DX11 due to required hardware features or API support requirements. Now, the custom backends let you use Fidelity Effects technology expressed in the terms of your own engine's abstractions and constructs. You provide just a few fundamental services, and all the plumbing and the logic for an effect component should just work. This allows you to unlock Fidelity Effects technology on any platform your engine supports, assuming it can compile shaders using a relatively modern shader model. Now let's look at a breakdown of what you'll find on disk when getting the SDK. Our SDK code folder is typically anything you might ship in your game or use to build your game. You can either compile the SDK into a set of libraries through the C API and link it with your application, or take the shader code directly into your game like you did with our old samples. Again, nothing is lost from the current situation. We've only added more on top to make things easier to use and introduce broader consistency. Building the SDK will make a set of static libraries, one for each component and one for each backend. Link the ones you want, leave the rest behind. The samples directory is where you'll find our new Cauldron 2.0 framework. This completely re-architected framework is built on the concept of render modules, which can be thought of as rendering feature nodes in a modern-day render graph. The render modules folder contains common render modules used by most of our samples. For instance, rendering a G-buffer or a sky dome, doing a transparency pass, or rendering particles. Each effect sample will also implement its own render module to demonstrate just how to use one or more of our effect components as you would in your own game. Lastly, we'll provide all documentation in various formats like CHM, HTML, and MD formats for easy browsing. Now let's have a look at just how simple it is to initialize and use the Fidelity Effects SDK using one of our new samples, Fidelity Effects Blur. The first step is to query the amount of memory you will need to allocate to back all the effect components you want to support. In this case, we're only backing the blur effect. Note here the DX12 part of the function signature. This is indicating that we are using the DX12 backend in this particular example. The next step is for memory to be allocated. Now, we put the burden of allocation on the developer so that you can use your own memory allocation and tracking schemes internally. Once your backing memory is allocated, the backend interface is initialized with it and the corresponding device object for the platform in question. Note that the backend will take care of incrementing or decrementing device reference counts for platforms like DX12 in case you need to track API interface allocations. Now, once the backend interface is set up, we initialized our effect context description. This tells the effect library how you would like to use the effect in question. In this case, we're creating a blur effect that will allow all kernel sizes to be supported dynamically and use the fast-packed math options in the shaders. Once the context is set up, we call ffx blur context create to create our effect context, and we're ready to start rendering blur. Using the effect context at runtime is just as simple. We first set up a dispatch context description to tell the library the desired configuration of the effect to use. In this case, we're requesting a 13 by 13 blur kernel-based operation at application resolution. We also provide a backing command list from the application for command recording in the library. We then import our input and destination resources from the external application to bind to the GPU workload. Then it's just a matter of dispatching the context with ffx blur context dispatch. When the application shuts down, or we're otherwise ready to stop using blur, we simply destroy the blur context. Please don't forget to flush the GPU to make sure everything is clear of the pipeline. And the last thing to do is to release the memory that you allocated to back the interface with. And you're done. Now let's take a brief look at how each of the main SDK components work together to enable Fidelity Effects features to run easily in your games. The first piece we'll look at is the effect component. The effect component represents the runtime level execution portion of a Fidelity Effects feature. This handles internal resource creation, external resource registration, the building of pipelines, creation and management of resource views, and GPU workload scheduling and execution for the application. These are essentially usability modules designed to make integration of the SDK features as seamless as possible. Should you opt to do direct integration into your game, you're going to want to replicate what the effect component is doing to ensure proper integration. Now, the source to handle all of this is grouped under 3 different levels. Public source contains all of our top-level common SDK include files. This includes the SDK interface, as well as things like errors, types, and utility headers, as well as the CPU host side effect header, which we'll look into more in a moment. Shared source contains platform hooks for assert definitions and convenience functions for resource and pipeline releasing. And private source is where you'll find the implementation details for the effect component, as well as header definitions for all private structures used. Now, the ffx effect.h file is the main file to include in your application to pull in effect support. You can either include the host side effect header directly or pull in ffx_fx.h, which contains all effect headers for easy inclusion. The effect header file is standardized across all of our effects and contains roughly the same information. Versioning information in the form of a major minor patch define, a context count requirement, which are used to figure out how much memory the backend needs to manage in order to have multiple effects working simultaneously. And we'll talk a bit more about this later when discussing the backends. Effect-specific defines to use in your application, pass enumerations, initialization bits if needed, an opaque effect context definition, which is mostly just a memory buffer that will back a private context, and context creation and dispatch description structures. These will vary on an effect-by-effect basis according to what is needed for setup and workload dispatch. Lastly, each effect header will define the main effect function signatures: context create, context dispatch, and context destroy. What they do should be fairly self-evident. As a note though, some effects, for instance FSR2, can have more functions exposed when additional functionality is present, like autoreactive mass generation. However, for the most part, most of our effect components only expose these three core functions. The ffx effect private.h file is where you're going to find all the definitions used in the implementation details for each effect component. This will include the multitude of shader permutation options used to create the needed pipelines, the CPU side constant buffer definitions that we use to upload constants, and private effect context, which holds everything used internally throughout the lifetime of the effect component. As an example, you can see SPD's private context definition here. Lastly, the ffx_effect.cpp file is where you will find the effect component's implementation details. The public-facing context create, destroy, and dispatch calls are largely just redirects into internal implementations, which is where you'll find the bulk of the feature implementation. Next, we'll have a look at how this ties into the SDK backend constructs. Now, all of our effects components rely on a backend-specific implementation of our Fidelity Effects SDK interface. This interface was largely derived from the interface model developed for FSR2 and expanded upon in order to properly back all features we currently support. The backends are API or platform-specific implementations of all required interface functionality, plus whatever code is necessary to make everything work. The SDK will initially ship with three backends: native DX12 and Vulkan, and a custom backend expressing the interface functionality in terms of our API-agnostic graphical framework, Cauldron. The backend, on top of implementing interface support, is also largely responsible for building all shader permutations for a particular platform. The files to enable this are grouped under 4 different headings, plus a special shader permutations project. We have public source, which contains the backend definition file that you're going to want to pull in from your game or application. This defines all the functions you need to call in order to set everything up to use an effect component. Public shaders has all shader language callback files. These are defined per effect for each shader language and serve as accessors to all effect resources and constant information. Public shaders also include all effect resource definition files and all effect pass implementation files in header format. Private source holds all shader blob accessors compiled with the pre-generated shader binary data that we export by the shader compiler tool, as well as the implementation details for the backend. Private shaders are all shader language specific entry points for all of our effect passes. Lastly, you'll find a shader permutations project that also gets generated alongside the backend. This is just a CMake project housing all of the rules we use to build all required shader permutations when building the backend. Lastly, let's have a quick look at the FidelityFX shader compiler. The FidelityFX shader compiler is an open source tool we're shipping alongside the rest of the SDK. Its main purpose is to compile all effect path shaders for a specified language with every permutation of option passed in. These shader binaries then have the reflection data extracted and written out to header files as a shader blob along with the compiled shader binary. Now currently, the shader compiler supports HLSL compiling via DXC and FXC when using DX11 backend, and GLSL compile via GLSlang. The tool is easily modifiable to support additional flags and options you may need for your game needs. Just be sure to copy the compiler binary into the SDK tools binary store directory, along with any needed libraries or DLLs if you make any changes. The precompiler is also easily extendable for new languages. If new language support is needed, create a new compiler class that inherits from our compiler interface, define a new shader binary structure, which inherits from our shader binary interface, and implement all compiler virtual functions needed to compile, extract, and write the various data out to file for inclusions in your own custom backend. You can then add an execution path to your new compiler by adding support for an additional language command line argument in ffx_sc.cpp. Now, let's take a look at the new graphics framework backing all of the samples in the SDK. The SDK samples are powered by an overhauled version of Cauldron, now at version 2.0. The entire framework was re-architected from the ground up to better support our development needs within AMD, but also to make it easier for developers to locate information while browsing our sample code. Now, this new version of Cauldron is highly customizable on a per-run basis, and was designed with emphasis on flexibility and quick setup and teardown. Cauldron 2 also implements all core components in an API or platform abstracted fashion to ensure support across all of our supported platforms. Cauldron 2 revolves around the concept of render modules, which are functionally like feature nodes in a render graph. Each render module is a fully contained plugin of sorts and has its own configuration and dependency file, HLSL shader source, which currently all shaders in Cauldron are HLSL based, and then cross-compile to either DXIL or SPIR-V as needed for DX12 or Vulkan. Contains any additional or optional dependent media, and then the source. Currently, our samples use a combination of the following render modules, which you'll find in the render modules folder: rasterized shadows, gbuffer construction, deferred lighting, translucency render, sky dome render, temporal anti-aliasing, GPU particle simulation and rendering, and animation support. The Cauldron framework itself also contains 3 exclusive render modules for core functionality, and these include a default tone mapper, a UI renderer, and a swap chain render module to control presentation buffers. Now, sample loading in Cauldron is handled via GLTF. We now fully support the 2.0 spec, allowing you to export your own content via a growing number of GLTF plugins and load it directly into our samples via command line for easy testing. As we continue to develop more advanced features, it's critical that we always ensure support for the latest versions of third-party APIs. In order to preserve constant forward momentum, each SDK release will also feature the latest stable version of Microsoft's Agility SDK, the DXC compiler, and DX headers, all of which will be in lockstep to the last stable Agility SDK version. We'll also feature the latest version of the Vulkan SDK. And other third-party software we use includes ImGUI, our AMD GPU and CPU services library, DX12 and VK memory allocator, STB image loading libraries, vector math, and a JSON library. Now, let's have a look at how our samples are put together. Each feature sample is built on its own self-contained framework configuration. The sample will contain one or more simple render modules showing how to interface with the SDK for that particular feature. The sample solutions can either be built on a feature-by-feature basis or as a master solution with all features. Furthermore, there are also scripts to build samples backed by either Cauldron's custom SDK or linked against native backend libraries from the SDK for DX12 and Vulkan. Initial release will feature updated versions of nearly all previously released Fidelity Effects content. A combined FSR sample featuring Super Resolution versions 1 and 2.2, Contrast Adapted Sharpening, or CAS, Combined Adaptive Compute Ambient Occlusion, or CACAO, Stochastic Screen Space Reflections, or SSSR, our Luma Preserving Mapper, or LPM, Parallel Sort, Variable Rate Shading, Single Pass Downsampler, or SPD, and Hybrid Shadows. Now, SSSR and Hybrid Shadows also have had their tile classifiers and denoisers grouped under new building block libraries. These are Fidelity Effects Tile Classifier and Fidelity Effects Denoiser. And both of these libraries have been updated with the latest bug fixes and optimizations to make their backing samples even better than before. Also shipping will be a few new feature libraries. And the first of these is Fidelity Effects Depth of Field. This sample features a physically correct, camera-based depth of field implementation optimized for speed. It makes use of tile-based classification in order to do fast path selection wherever possible. The near and far blur operations are handled through a single pass dispatch, as are the combined filter, upsample, and final composition steps. The entire effect works as a combination of 5 passes: depth and color downsampling, a dilation pass, a blur pass, and a composition pass. Our Fidelity Effects Lens sample is a highly optimized single pass shader that supports some of the more commonly used lens effects in video games. This includes film grain, chromatic aberration, and vignette. Now, this is just an initial sampling of lens effects, and we plan on adding to the library in the future to continue to support basic render effect needs. And our last new sample is Fidelity Effects Blur. This sample features a highly optimized set of blur kernels that can run from 3x3 to 21x21. Now, the sample also features a comparative diff tool to allow you to see the difference between the Fidelity Effects Blur kernel versus other common blur approaches like single-pass box filters, multi-pass separable filters, and multi-pass separable filter transposes. Now let's wrap things up. The Fidelity Effects SDK is currently available in beta form to our NDA partners for evaluation purposes. Please look forward to its public release with a port of all existing samples and our 3 new lens-based effects. We're also planning to release a 1.1 point release sometime later this year. This will contain an Xbox GDK backend, new Fidelity Effects samples, Cauldron improvements, as well as scene interaction support. We're also planning a 1.2 point release at some point later on towards the end of the year. This will have further feature improvements as well as more new Fidelity Effects content. And of course, as always, you are welcome to take our code to integrate directly into your own games and or modify it as you see fit for free with no vendor-based restrictions. Now, in the last years since we've begun putting out Fidelity Effects features, we've become one of the most used and trusted technology partners in the industry. Our first-in-class open-source technology can now be found in over 250 games made by some of the biggest names in gaming. In summary, the Fidelity Effects SDK offers the same great technology that developers have come to expect from us, now just a little more consistent and easier to use. The SDK will be the delivery platform of choice going forward for all Fidelity Effects features. We're shipping all of our previously released features, plus 3 new effects and new graphics building blocks in the form of updated tile classifiers and denoisers. All of our effect integration is now backed with easy-to-use C APIs to take the pain out of supporting the features that you like. A modular backend that puts you in control of how your engine backs our effects. and complete and thorough documentation on all of our underlying code and structures. Finally, a great new shader compiler tool to front-load all shader binary generation. Now, the Fidelity Effects SDK is the culmination of many months of work involving many people in game engineering here at AMD. So I'd like to just take a brief moment to thank all the people who've had a hand in helping to push the SDK over the finish line. So please look forward to the public release of the Fidelity Effects SDK.